Okay, energy change in a chemical reaction. So we talked before about how we can figure out, based on calorimetry, what some different energies are in different chemical reactions. In this case, we're going to talk about if we know all the delta H of formations of the elements in a chemical reaction, how we can predict the delta H for that reaction, or we can predict the energy change for that reaction. Just as an example, so we have something to talk about, I'm going to use a simple reaction CH4 plus O2 goes to CO2 and H2O. So those are all pretty common chemicals. I should be able to look them up from charts. Their states do matter here, so we're going to assume we're predicting gaseous, or we're producing gaseous water in CO2, and that these guys are gases as well. So now, using a chart, I can look up the delta H of formation of all of these different things. So this is alphabetical. If you're using the textbook we happen to be using, it's on page 799. But you could just look up a chart on the internet for these pieces of information. Methane, CH4, happens to have a delta H of formation of negative 74.4 kilojoules per mole. What does that mean? That means if you took C and H2, its elemental form, and reacted it to form CH4, so we'd need two of these, we're going to produce 1 mole of this, that because that's negative, that means 74.4 kilojoules of energy would be released. So if C and H were both at the 0 energy level in the first place, when they went to form CH4, they would go down by 74.4 kilojoules to a lower energy state, releasing this energy to the environment in an exothermic reaction. I'm not going to write that out for each one of these things. I just wanted to review that basic definition on my way by there. Okay, anyway, not getting too distracted by that. O2 is in its elemental form, so that's nice. I don't have to look that one up. That one's delta H. It's going to be 0. CO2 I can look up. I need to make sure, well, carbon dioxide will probably only be stated as a gas. So, negative 393. Kilojoules per mole. And with H2O water, I got to be careful because I bet you this is going to be stated as a gas or a vapor. And since I said that I'm getting a vapor, I'm getting a gas here, I'm going to use the number delta H of formation as negative 241.8 kilojoules per mole. Oh, what did I do here? So I know this is where CH4 is at the beginning. And I know and O2, it's up at this level, negative 74.4 kilojoules per mole. And I know after the reaction, it's going to drop to these levels, negative 393.5 kilojoules per mole. And, I need to be careful here. I need to represent how much of this reaction is actually happening. So back when I was doing this, I got a little ahead of myself and I forgot to balance the chemical reaction. 4 hydrogens are going to 2 hydrogens, and 1 carbon dioxide is going to 1 carbon dioxide, and then there's 2 oxygens. So there's the chemical reaction balanced. That's important because I'm not producing 1 gas molecule down here. I'm producing 1 water molecule. I'm producing 2 water molecules. So 2 times negative 241.8 kilojoules per mole. So I'm going to go from 74.4 all the way down to all of this. So let's figure out what all of this is. 2 times 241.8 plus 393.5. So this level is negative 877.1 kilojoules per mole. So now if I want to know what this delta H is, I started at 74.4, so I'll call that delta H of my reactants. And I ended here So I'll call that reaction. So I started with my reactant. Oh, okay, this is confusing. Let me try this again. Hold on. So if I want to know what my delta H for my reaction is, what my change is, I could say it's my final situation minus my initial situation. This represents the products, and this represents the reactants. So instead of saying 2 and 1, I could say products and reactants. And so my delta H for my products in total is negative 877.1 kilojoules per mole. And for my reactants was 74.4 kilojoules per mole. So my total change is 877.1 less 74.4, or this is negative and negative, which works out to be a positive. Anyways, the change here is 802.7 kilojoules per mole. Negative. So the reactants have gone from this energy state way down to this one, and this is the energy that's available to the environment as an exothermic reaction. I didn't have to do all of this and show it all in all of these steps. I could have just taken this minus this and done the calculation directly. I just did all this to be instructive. So delta H here for a reaction, if we just want a simple formula which represents what I did all of here, would be the delta H of the products minus the delta H of the reactants. Again, I just did all this to show why, right? It started in this hole where the 74.4 came from the CH4, and the O2 was at our zero reference level, and it went down to CO2, which is way further down than our reference reference level, and two 241s. So all the way down to that 877 level, the change that's available for energy then, delta H, worked out to be 802.7 kilojoules per mole. If you look at further examples of this, there's going to be more and more where we tie it further and further, but that's how I get the delta H from a reaction, assuming I know the delta H's of formation.